And the last speaker before the poster presentations is Benjamin Wehmeyer. Good. And he will talk about galactic chemical evolution of the R-process elements. Go ahead.
Yes, thank you very much. First of all, I'd like to thank the organizers for a very nice conference. Fantastic to be here. And yeah, giving me the chance to also contribute some little thing. I was originally scheduled to Monday, but I couldn't come on Monday, so I had to do this presentation today. But when I checked the slides of Monday, I saw two very nice slides, and I asked Alexander Heger whether I could also show them today. And he showed these two slides. So the first one was what the Big Bang made, the primordial nucleosynthesis abundance patterns, and what we find today, so the solar abundance pattern. And the interesting question is, what happened in between? And my field, galactic chemical evolution, might help to solve the puzzle, what happened in between. And so if you go to an evolution curve, for example, here we take magnesium, which is a very smooth alpha element. We can see, well, it evolves very nice. The spread of abundances is not too large. So maybe in total 1 dex of spread. And it evolves very nice until Fe over h to -1. Until supernova 1a will kick in and eject large amounts of iron. And then the abundance curve will shift down until 0, 0 is reached, which is solar metallicity and solar abundance. And this notation, if you're not familiar with it, x over y in brackets, means the log of x star over y star considered, divided by the normalization, so x of the sun and y of the sun. So this one is really nice and quite well understood. But on the other hand, if we consider R-process elements, and europium seems to be an R-process element that is very nice as a diagnostic because it seems to be relatively easy to observe for astronomers. And we take this as a diagnostic for the evolution of R-process elements. But we see here right away that the scatter in the beginning of the abundances is very, very large. So it's 2 dex, whereas at solar metallicity, on the very right one, it's relatively small. So if we plot one on another, then we can see right away, so the blue field here is 95% of the magnesium abundances, and the red points are the europium abundances. We see right away that it is totally different behavior. So at very low metallicities, we have a scatter that is really large compared to standard alpha elements. So what we know from theoretical supernova calculations, but also from these considerations, that this cannot be the same site where it's produced. So from some discussions that I had yesterday evening, I was asked to also talk about a little what the chemical evolution model does. And so I want to make a little intermezzo here and want to explain what we are considering here. So on the very left, you see the interstellar medium. And if the conditions are fulfilled, then we can produce stars, and stars burn. And if stars are light, then they, when their nuclear fuel is burned, then they will emit, they will end up in planetary nebula, giving back their mass to the interstellar medium again. Or if they are heavy, or they might do supernova 1a, and also giving back matter to the interstellar medium. Or if they are heavy enough, they do a core-collapse supernova and give matter back to the interstellar medium. Or if it's a double star system and 2 neutron stars orbit each other, there might be a neutron star merger, also giving matter back to the interstellar medium. But this one is process abundant. So let's set up our galaxy. We take a cube that has an edge length of 2 kiloparsec and divide it in subcubes with 20 parsec edge length. And then we do an infall of matter. We read the local density. Then we can calculate the star formation rate. And in high density regions, we have more star formation. In low density regions, less. And we calculate an IMF, which says, OK, this is an IMF here, which says, OK, how probable is it to generate a star with a certain mass? So it's very improbable to generate a high mass star, but it's quite probable to generate a low mass star. Then we can calculate the estimated lifetime, where Z is the metallicity of the star, M is the mass. And we get the lifetime. Yes, then we add the local interstellar medium enrichment to the star and check whether some stars have reached the end of the lifetime. Then we simulate the explosion, shift the matter away. Or if it's a double star neutron star system and it reached the end of the lifetime, we also simulate an explosion. So the stars considered, either they are quite lightweight, they are below 10 solar masses, they don't produce supernova elements, they will, at the end of their lifetime, reject the matter to the interstellar medium. If it's heavier than 10 solar masses, it's doing a core collapse supernova. And when it's in a double star system, and we can calculate the probability for that, it can later do a neutron star merger event after a waiting time. Or if it's other prerequisites are fulfilled, we can do a supernova 1A. There's also a probability on that. That is normated to observations. So when considering the classical R process side, which is neutron star mergers, and here is an illustration from Rosvog, who calculates this since a long time. We can see the two neutron stars spiraling inwards and later getting together. And the color represents the fate of the matter. And we can see that the red portion of the matter will be ejected back to the interstellar medium. And this matter, the red one, will be R process enriched and thus polluting the interstellar medium with R process elements. When we now set up a simulation environment that uses neutron star mergers only as R process sites, then well, the different colors represent different simulations. So we can either represent the high metallicity and reproduce the solar or close to solar europium abundances. And green, and the difference between green and red is the in-spiral time, where I think red is 1 giga-year and green is 10 mega-years. So it's not so much of a difference. But we can see that both these curves will not be able to reproduce this low metallicity end here. Whereas if we increase the frequency, which still is in the observational limits, on theoretical limits, we might explain some of them here, but we totally fail here. So let's consider a second side. What you see here is a simulation of our group where we simulated magneto-rotationally driven supernova, which comes from a highly magnetized and fast-rotating progenitor. And white are the magnetic field lines, and the colors represent the entropy. And in these jets that emerge from the core and are ejected from the poles, also nucleosynthesis calculations were performed, and they also successfully reproduced an R process pattern. And since this one actually derives, does the R process nucleosynthesis directly at the supernova, the interstellar medium will not be enriched by metals before, and then we have to wait for this waiting time until the two neutron star mergers unite. No, they will directly eject and simultaneously eject the R process and the iron. So we go again to our GCE simulation. And when we consider here a simulation that only consists of these magneto-rotationally driven supernovae as R-process sites, we can make the same considerations as with neutron star mergers. We see here we might do it, but here we fail. And if we choose parameters that reproduce the europium abundance here, we fail here. And the other way around, if we decrease the frequency of the magnetorotationally driven supernova. So, what do? We will establish a combined environment with both the magnetorotationally driven supernova and neutron star mergers. And if you choose the perfect parameters, then you can see which are actually 0.1% of the core collapse supernova, which means every 1,000th core collapse supernova will actually perform a magnetorotationally driven supernova. And you can see it really nicely reproduces the observed abundance curve. So we can reproduce the scatter at very low metallicities, but also the quenching of the scatter here, and also the second quenching of the scatter that occurs over here. This lets the question arise, why is there a scatter at all down here? And this comes from inhomogeneities. So in the early galaxy, there were probably very strong inhomogeneities. And if we look at different stages of the galactic density histogram, then we can see at very early stages, which corresponds to this marker here, this one, we can see that the interstellar medium is very inhomogeneously distributed. And this marker here corresponds to this, and this to this, and this to this. So the later we get, or the higher in metallicity, the more well-mixed is your galactic halo, and thus the interstellar medium. And so with this, we might explain why there is a big scatter here and this small scatter here. So for instance, if you take this one here, then it's very important whether your newly born star will be created here. If this was a magnetorotationally driven supernova, then he will have a very high abundance in europium, or if it's born outside, it will have a very low abundance. But later on, for instance, in this one here, it's not so important whether your newly born star is put here, or here, or here, or here. And thus, it's not such a large spectrum of possible abundances that the newly born star may inherit. So a different point is when considering alpha elements that with the canonical core collapse supernova yields from Tiedemann 96 or Nomoto 97, then we will realize that maybe the spread in oxygen might be a bit too large at lower metallicity. The same is for magnesium. But we know that the iron yields are not so well defined, and if we just to test artificially reduce the iron yield to 0.5 of the alpha yield, we might even get a straight line until the 1As kick in for sure, but we get a straight line, so no scatter at all. So there might be a problem with the core collapse supernova yields, which says that these really have to be improved still. So one possibility to solve this, Chiaki Kobayashi, who was also in the audience, provided me this year with her metallicity-dependent yields. And if you use these, then you are able to maintain your scatter and keep it so maybe below 1 dex until quite high metallicities, until the 1As kick in. So we have really nice behavior on here. So this brings me already to my conclusions. Neutron star mergers alone have difficulties to explain the abundances at low metallicities. An earlier site is needed for this, in the halo at least. The spread in R-process elements at low metallicities can be explained by inhomogeneities of the galactic halo. And yields from supernovae still have to be improved. They have huge impacts in the GC. With this, I'd like to thank you very much for your attention.
Before we start the question session, can the poster presenters please line up? Thank you. Other questions for Benjamin? Yes? Gabriele?
Can you explain your model also the spread for strontium over barium?
Yes, I know it's a different behavior here. I'm working on this, yes. Up to now, no. But I hope to do this later.
Other questions, comments? Yeah, Tim?
Yes, very nice work.
Thank you.
Helpful conceptually. So when you made your mixture, I presume it was dominated by what, the magnetic MHD at the very earliest time and then slowly changed over to something that became dominated by neutron star mergers? Is that a correct interpretation?
Yes.
Okay, so one could actually begin to test that against extant data on the, for example, metallicity distribution of the highly R process enhanced stars, R2, versus R1, which cover a different metallicity interval. That's one of the keys. And also, I'd be curious to know if one or the other of your progenitors could specifically be associated with the actinide boost. Because that 1/3 is a good solid number. It's getting better, but that would tell you if you could reproduce that with one but not the other.
Yeah, it's a great suggestion. Thank you.
A final question? If not, let's thank Benjamin again.